All right, so now let's look into deriving adjoint rules for more complicated instances, right? So let's look at some implicit equations, right? So let's say we have things like nonlinear solve or the or linear solve that show up inside of our program. We want to be able to do backpropagation over them, so we need to derive all these primitives, right? So let's say someone has a backslash b inside of their program. What do we do with this, right? So when we go over it, we solve a backslash b, and when we go backwards, what is that function, right? What is the function here that we define for how to tell it to go backwards, right? So let's actually look at this in isolation. So the problem of linear solve is, you know, a is possibly a function of parameters, x equals b, which is possibly a function of parameters, and we solve for x, right? This is the problem of a nonlinear solve. Um, Now let's say we have g of xp as some cost function that comes after it. So the derivation of adjoints usually happens with a cost function, but there's going to be a trick that I'll show you that kind of brings it back to reverse mode automatic differentiation. So let's assume that you have a cost function on the output of a linear solve, right? So you calculate the solution of the linear solve, and then you would apply the cost function to it. That would tell you the cost, and you want to minimize the cost, right? And so what you want to do in order to find the right parameters to make the solution X be, close to data or something, um, what you'd want to do then is you would want to take the gradient of the function g with respect to p, right? Where changing p changes the matrix and changes the vector, so it changes the x that you solve for, and therefore it changes the cost, right? So this is the way that we're going to phrase a lot of our adjoint problems. There is a cost function on the solution to this mathematical problem, where the portions in the mathematical problem are defined by parameters. We want to figure out how to calculate the gradient of that cost function with respect to the parameters. So how do we do this? Well, let's just start writing out chain rules. That usually helps. So here what we're going to do is we're going to say dg dp equals g sub p. This is just a chain rule. G sub x sub p. Right. If you need to write this out a little bit more, what this is saying is that this is partial g partial g partial p plus partial g partial x and then dx dp, right? This is what and you cancel, and yeah, you can't actually cancel, but this is where it comes from, right? So the way that I'm writing my partial derivatives here is just g sub p, so that's partial g partial p, because otherwise there's just going to be way too much notation. So you might know this kind of notation from PDE literature, so partial differential equation literature, writes partial derivatives like this all the time. So this is the partial derivative of x with respect to p. So okay, right. So you normally think of x as a constant, but in reality here, x, since it's the solution to this linear equation, it itself is a function of p, so it's differentiable with respect to p. Okay, so let's actually write down what this is going to be, right? Well, we know that if this is our linear equation, then we know what the solution is, right? So the solution is going to be that x is this function of p, which is going to be a inverse of p, right? So I'm going to drop these function call points. Just kind of remember in your head that everything's a function of p here, right? So that's the solution to the linear system. I hope you know that. Otherwise, you are in the wrong class. So okay. So let's do the chain rule on this then, right? So to do the chain rule on this, what we do then is we say, well, we do the yeah, sorry, that way of deriving it is not as straightforward. Here's an easier way to get to that expression. What you can do is you can just say that ax equals b, right? That's what we're solving for, And now you can take the derivative of both sides by p. So you just say by chain rule, derivative of a by p x plus the a x derivative by p equals b derivative by p, right? That's just the product rule. And now you just rearrange, right? So you have that a divided by, or a sub p x plus equals b sub p, or no, you move the other term over, right? So a x sub p equals b sub p minus a sub p x. And now this is where you say, okay, I'm going to then invert a. And so therefore you get this expression right here, right? So that's how you get the derivative of x with respect to p. It's easiest just to take the derivative before doing modifications and then modifying it over. All right. So now the difficult part is that this requires doing p m by m linear solves, or it requires taking the inverse of this really large matrix and multiplying it to a big matrix to make an even bigger matrix. This is not necessarily the most efficient way to compute this. So there's a trick that you can do. You can introduce this quantity right here. And this is literally just a trick. And I think that it will make sense the second and third time that you see the trick. So it's okay if it kind of comes out of nowhere here. So we say that lambda sub t, which is some kind of Lagrange multiplier kind of thing, we say that this is going to be equal to this. So we do this by ansatz. We just kind of say, this is what it's going to be. Turns out that this is the solution to the solution to this is that a equals a inverse b, right? So this is a kind of a form of a vector Jacobian product, so there you go, like that's where it's coming from, right? It's a vector Jacobian. We're looking at the Jacobian here of the actual solution. So okay, but but we can also think about it as this is an ansatz. I just kind of take this guess out of anywhere. Now let's look at this, right? So what we want to do is we want to take dg dp, right? We want to take the derivative of the cost function at the point where I'm going to say that the solution, f is the function that computes the solution to the nonlinear solve. I want to take the derivative of the nonlinear solve at its solution, right? That's what I'm saying here. Like the f is the residual function, right? So on this, we can say that f of x p equals a of px minus b. Right, so f is the residual function, and so the derivative of the cost function, since the cost function is, with respect to the solution of the linear system, it has to be when f equals 0, because that's when the x is the solution to the linear system, right? Otherwise, there's a residual in there. So what we can do then is we can say, well, let's actually just write this out. So this is g sub p minus lambda. If we actually just write down dg dp and evaluate it at f equals 0, right? So what we get here, right, is we have this g sub x, x sub p, where let's actually just plug right in what this x sub p is. We have g sub p minus g sub x, and then this old baddie. Let me move this down, actually. All right. So we got that whole bad boy there. And then now we're saying that we're going to make this be a substitution. And so we do g sub p minus lambda transpose times f sub p, right? So this is the derivative of the residual function. This is the derivative of the residual function at the point P, and we want to do this when f equals 0, right? So what you do is you find the x for which f equals P, then for that x, then you take the derivative of f with respect to P, and that's what goes right here. Right? Or you can plug it in, right? So you could plug in this right there as well, and that would be these are all equivalent ways of thinking about it. Though that second way of thinking about it will come into play quite soon. Right. So you take the derivative at the point where f equals 0, and then you multiply it by lambda, right? So it turns out that this is the way to be able to write down the adjoint of the linear solution, and it doesn't really do all that much because it doesn't really change your computation time much at all. It's kind of like you're moving around parentheses and such, but this is what you get to, right? So what you see is that when you're going in reverse, right, you do essentially what you if you multiply a on both sides, right? So then what you're doing is what you're effectively solving is lambda transpose a equals g sub x. But if you remember what g sub x is the derivative of the output with respect to x. You look back at our previous notes, that's one of those things that you'd recall as a bar term, right? So this is the value that you'd actually get from the pullback, right? So g sub x is the bar value that would come from the pullback. And so when the pullback gives you something, then what you do is you solve the linear system for the transpose, right? So let's transpose both sides here. Right? So if I transpose both sides, then this transpose goes away. Here's a transpose. Here's a transpose. And oh yeah, when I do a transpose, I flip. Here's another ax plus, equals b problem. And so the adjoint of a linear solve is you solve this linear system for lambda, and then your pullback is defined by once you have lambda, then you stick this right in there. All right. That's weird. Can we see it? You can. So let's actually dig up the zygote.jl library. So here we go into, let me show you where I went to for this. So inside of the zygote.jl automatic differentiation library, I go into the source files, I go into the lib, I go into the array file. So these are all of its overloads for the arrays. And if you look in here, you'll find that when a is square, there's a simple adjoint method, right? So let's go look at the simple one. And so what is the adjoint for backslash? Backslash, right? Backslash is the solution to, so a backslash b is the solution to ax equals b. This is what we just derived, right? So what you do for the adjoint is in the forward part, you calculate the y is equal to the solution of ax equals b. So, call this y, right? So y is x. Now what you do is you write a pullback function, or what you do is you solve a linear system for a transpose backslash pullback, right? And this gives you this lambda term. And then after you've defined this lambda term, you have the derivative with respect to a and the derivative with respect to b. Now, what is the derivative with respect to b of b? Well, that would be this term right here, right? So yeah. So then you have, so you can work out the next details. So, but basically, then you'd go one step back and you'd say the way that you would turn derivatives of cost functions then into derivatives of the inputs and outputs is you would say that my cost function g of xp is equal to x, right? So once you say that your cost function is the identity function, then the output of the linear solve is, the output of the cost function of linear solve is just the output of the linear solve. So now this adjoint method becomes something about the derivative of the output. So it's kind of a weird trick to kind of think about, because when you do this derivation, you need to have a function in here that you usually call the cost function. But if you call this cost function the identity function, then what you can do is you can say, okay, this is my identity function. That's why g sub x is the pullback value, right? Because this is just dg, or essentially, that's that weird one that showed up in the previous derivations. This is where that one or that pullback vector choice shows up, right? So this term would cancel out, and essentially what you do is you can rewrite then your derivative with respect to A and the derivative with respect to B in terms of this lambda that you quantify, right? And that's where this derivation comes from. And then you can work out the last detail in there, except I want to move on to the adjoint to the nonlinear solve, which to me starts to help it make a lot more sense. So I know I'm going through the adjoint to the linear solve quite quickly, but I feel more comfortable with the nonlinear one, and then you kind of get out of the nonlinear one. A special case is the linear one. So let's see. So how do you do the adjoint to the linear solve? What you're doing when you're solving a nonlinear function is you're solving f of x p equals 0, right? Where f is the residual function. And so you could clearly see how this is going to be a extension to it. So how do we do this? Well, let's take the derivative with respect to p. So f sub x, x sub p, f sub p equals 0, right? So this is so if you rearrange here, what you get is that x sub p equals minus f sub x inverse f sub p, right? Except you have to take the derivative somewhere. That derivative needs to be taken at the point where the nonlinear system is satisfied, right? So, okay, so let's assume we have a cost function, right? This cost function will end up being the identity function again, but let's assume we have a cost function. So let's, so we have a cost function g of x p, where once you know what x is, then you stick x into this cost function to be, and this is the thing that we want to take the derivative of, and this is the thing that we want to take gradients of, right? So, for example, you can do like the sum of the x's, and we want to then minimize the sum of the x's, where the x's are a solution of the nonlinear system. So the way that we write down the derivative of this cost function is dg dp equals, g sub p plus g sub x, x sub p, right? Just another chain rule. And how do you write down x sub p? Well, it's just this thing right here. And we have to flip the sign, right? Okay, so, well, we have commutativity, right? So technically, this is true, and technically, this is true. That, let's remove here, and now let's stick these in parentheses. Right, they're both the same thing, so both of them are true. But it comes down to the sizes, right? So if we have m state variables and p parameters, right, and we're looking at a Jacobian, right, when we take, when we take the derivative with respect to the x's, then and assume that we have, a square system here. If we take the derivative with respect to the x's, then the size of this Jacobian is only based off of the states. If we take the derivative with respect to parameters, then we have, dp1, dp2, dp3 as all of these different columns. Right? And so if we, so this matrix is m times p, whereas these other matrices are based just off of the size of the state. And so this, if we were to ever do this operation directly, we would get a fairly large system, and then we'd have to make a smaller system. But one way to be able to avoid making the large system is we change our parentheses and we combine the terms to make something smaller first, and then we make it, we keep things small instead of growing and then shrinking. And that's really the key here, right? So essentially, what we can do here is, remember that our trick is always we never want to write down a matrix inverse, right? So if we say that g sub x, if we say that this equals some term lambda, right? Then if we multiply both sides by f sub x, then what we get is we get this we get this linear system. Or what we do is we say that this is going to be, let me write that down with the transpose. So the transpose always just naturally shows up in these. So what we say is that this is, let's define this as lambda transpose, right? Just like when we did the linear system, we define a lambda such that something's going to work out. So when we define lambda like that, then we have that gx equals lambda transpose f sub x, or this is also equal to f sub x transpose lambda, which is just then a linear system solve for lambda, right? So or f sub xt lambda equals g sub x, which gives us, by substitution, right, that once we know how to calculate this, we know how to calculate this because this is equal to lambda, right? So now what we have is dg dp equals lambda here. Right, so lambda is a vector, right? And so here's how we do this now, right? So instead of doing the inverse of this matrix and building a gigantic matrix and doing all this, we have a two-step process. What we do is we solve a linear system using the transpose of the Jacobian to calculate lambda, and then we multiply lambda by f sub p. We subtract that off from here, and we're good. So this is an exceedingly cheap formula. This has to do a linear solve using the transpose of the Jacobian. But again, this is going to be right here is actually where you start to see that vector Jacobian multiply. And this derivation, I think, is a bit cleaner. One of the things that you can think about then is if my original nonlinear system was linear, what would it look like? Well, if my original nonlinear system was linear, then the Jacobian of the Jacobian would be just let's write that down. I'd have that f of xp equals ax minus b. And so the derivative with respect to x would just be a. And so now you would have gotten a lambda equals gx. And you see then that what we did before was just a special case. Right. And that's why that kind of f of p above kind of shows up. Naturally, I think that the adjoint just works better in the form where you're talking about the residual of a nonlinear function. So it kind of oddly falls into play here, but it much more naturally falls into play in this derivation, I think. So okay, if we want to take the derivative of a cost function with respect to a derivative of the cost function written on the output of a nonlinear solve with respect to the parameters that define the input, that define the nonlinear solve function, what you would do is you would first solve the nonlinear system, right? So what are the steps? You would do one, solve the nonlinear system. f of x p equals 0 for x. Right, then what you would do is you would calculate f sub x, and then g sub p and f sub p. So actually, you can, these things are generally going to be easy. This f sub x, right, is the Jacobian of the nonlinear system with respect to x. You've already calculated f sub x if you did a Newton method, right? This is exactly that same Jacobian, just to make it clear. All right, so then what you do is you would solve. Oh yeah, and if g directly shows up inside, if x directly shows up inside your cost function, you put that there. Or if you have a pullback value, like if you're putting this into a reverse mode automatic differentiation system, that pullback value would be this g sub x. So okay, then what do you do from here? You solve, the linear system for lambda, and then after you have lambda, you explicitly calculate that, and that's how you get the derivative of g with respect to p. Right, so let's actually look at one of these examples then. Let's say we have f of xp equals to, I don't know, like 2x plus p, right? So the step one would be, step one would be to find that 2x plus p equals 0, and so x equals minus p over 2, right? And then step 2 is going to be, you calculate that f sub x equals 2. I want to do a cost function here. So g of xp, I want this to be, let's say x squared plus p. Right? Let's just have a p and an x that shows up in here. Right? So step one is we solve the nonlinear system and get x, and then we stick x in there. So then g of xp equals, it's going to be p squared over 2 plus p equals, you can't simplify that anymore, right? So the reason why you have a cost function and f is because, remember, f is implicitly specifying what x is, and then g is specifying what the function that comes after, right? And the reason why we need something that comes after is because that's what we're going to use to identify how we're going to do a backpropagation, right? How do we use the information that comes after us? And that's exactly why this is going to be the backprop vector, because it's the information that comes after our current call. Right, so now what we do is we calculate these other terms, and we say that g sub p equals 1, f sub p equals 1, and g sub x equals 2x, right? Now we solve the linear system. Step 3 is going to be that 2 lambda equals 2x, and so lambda equals x in this case. And then step 4 is going to be that fraction dg dp equals 1 minus x, right? Because lambda equals x, and then f sub p, which is 1. And so the derivative of g with respect to p is 1 minus x. And if you look at our analytical solution for here, and you do the derivative here, right? Let's actually calculate that out. That's just going to be dg dp equals 2, right? So that's 2p over 2 plus 1, right? So this is just going to be, did I mess up did I flip a p and an x here? I'm not going to. I'm not going to just stop the lecture to take too much of a look at that, but if you do calculate this out, you should get exactly the same thing. But if you do a direct differentiation, given that you can write down the analytical solution in this case, um, yeah, it's a bit odd, but I think I might have just made a quick error there. Because it's off by 1/2, right? I think that I just forgot to push a 2 in here somewhere. Um, it's off by 1/2, but I made some issue in there, but you should be able to see that you get to the same result in the end here. Sorry about that. It's extra credit to find an example like that. But okay, so why would you use this crazy way instead of just taking the derivative here? Well, for most nonlinear systems, you can't actually write down, you can't actually write down the solution to the nonlinear system to then be able to plug it into the cost function and then be able to take a gradient, right? That's the only reason why we can actually, in this case, actually calculate it out. If you can't do that, then you're out of luck, right? So this gives you a path to be able to, in a four-step process, you solve something that you can solve numerically, you do something that you can solve you numerically put this into the function, you numerically take these derivatives, you then solve a linear system numerically, and then you plug into this last equation numerically, and you get out this numerical derivative for dGdP. And if you've done it like this, you will have avoided putting your two largest terms together, and so you never get a m by p linear system that you have to handle. Because you never get an m by p linear system, it turns out that the order of operations here is m plus p, so the number of the size of x plus the size of p instead of the size of x times the size of p. Remember that everything that we did with forward monotomic differentiation, we got a m times p size, but here we have m plus p. So that's nice. And this basically shows the way to derive adjoints, that you define the implicit system that you're trying to solve, you define the cost function on that system, and then when you work through it, you find a vector Jacobian multiply and some linear solves in the middle, and then you use that to pull back to be able to get the derivative with respect to the cost function. So now let's do that for the ordinary differential equation. Again, adjoint derivations are all about tricks. So what are the tricks that we need to do to make this one work? So let's actually put a title on here because this will be a big one. Oh, adjoint of ODE. So let's say that u prime equals f of u t, just like the same notation we've been using all this course. And we have g of up is a cost function on the solution. What would it mean to be a cost function on the solution of the ODE? Well, ODE is its solution is something over time, right? So you need to have that cost function written with respect to time somehow. The way that we're going to do that is we're going to write it as the integral over that. So we're going to represent g of up as equal to some g. So it's a cost function on the ODE solution, which is an integral of some cost function at each point of the ODE solution, right? So at every point in time, we have some cost going along with our ODE. We want to kind of sum over the cost at all points in time. So here's how we're going to do the derivation. It's once again just another trick. So the nonlinear solve one was really just a trick of let's change parentheses and then define the the linear solve for the parentheses change. What's the trick here? So what we're going to do is we're going to introduce a Lagrange multiplier. So the integral of the cost function with respect to p is equal to g of p minus the integral of. I'm going to write this down, and then I'm going to explain a little bit. So this is f of u dt et. And now you're going to say, Chris, that makes no sense. We know that u prime equals f of u pt. That is the definition of the ODE. And so for every t, this is equal to 0. And I'm going to say, you're right. At every single point in time, this is equal to 0. So this integral right here is equal to 0. And so therefore, I of p equals g of p. Adding 0 is a great trick. So okay, let's look at this a different way then. Let's look at dg dp. This is the thing that we actually want to calculate. We want the derivative of our loss function or our cost function with respect to parameters. The way to get that is we can take the derivative of our of I with respect to p, because I is exactly the same thing. I is g plus 0. So we can do that. And now let's write this out. So it's the integral of t0 t g sub p plus g sub u s. So let me define something here. I'm going to use the shorthand s equals du dp, because otherwise du dp is going to show up everywhere. And we kind of want to treat du dp as a variable here, right? This is the thing that we're solving for. It's a function of time. You know, the derivative of the solution of the ODE at every single time point, that derivative with respect to a given parameter. There could be multiple parameters, but take the assumption there's only one. The same derivation would hold when there's many. Right, so if we do the chain rule, you know, so we take the derivative of the integral, we swap the derivative into the integral, assuming that the ODE solution is sufficiently nice. Then we do then we do the chain rule here. So this is remember that this is du dp, because this is dg du dp, and so this is where this s comes from. Right, that's where that term comes from. And now I also has this thing, so let's just kind of slap this thing on here and take the derivative with respect to p. So yeah, so that's not a function of p, so let's do d u prime dp. Well, this is just, you know, swapping derivatives again. This is du dp prime, and so this is just the sensitivity prime, right? So now we do the chain rule here, which is just going to be f sub u. So df du, du dp, which is just another s, and then df dp, which is f sub d. Right? And so this is getting closer to our adjoint method. Okay, so now we do another trick. So our trick is going to be that, remember integration by parts, right? So integration by parts, think of it, the way to think about it when you're doing these more difficult derivations is it's the derivative swapping rule, right? So if we have a term with a derivative and we want to make that, we want to take the integral of this term and we want to swap the derivative over onto this term, we would evaluate at the boundaries and we would minus and swap the integral, right? It's the derivative swap rule. Right? So now I want to make everything have an s in there. I'm going to show you why in a second. I want to have everything have an s in there. So let's do the derivative swap rule. So let's take this out in isolation. So we have the integral t0 to big T, lambda asterisk s prime, right? And now we do the derivative swap rule, which is going to be that we evaluate this at lambda asterisk. So we take the integral of both terms and we evaluate it at t0 and t, right? And then we swap the sign and we swap the derivatives. asks prime and asks, right? So that's where that comes from. So now let's see what we got here. So this is dgdp, right? Even though it's didp, but those two are the same things because they're just added by 0. So okay, so let's take this here, and now let's take minus this doodad, except we want to pull this out. And now let's swap the sign in here. And the reason why we pulled that part out is because we're going to do a minus and a plus. Right, okay. So we've just been rearranging terms. That's about it. And now let's rearrange all of our terms some more, and let's put everything with a s together. So let's move this out over to here. That has a dt. And now let's minus the boundary terms. I think I might have got sign wrong here. I'm going to figure out in a second. But now let's see. Now let's gather all of our s terms. There's going to be it's going to be an integral from t0 to capital T of lambda asterisk prime plus f sub u lambda oops lambda asterisk f sub u plus here's my other, right? So plus g sub u, and this is all times s dt, right? Now I think that there should be a sign difference in here. This should be, so I had minus here, minus, minus, so this would end up plus. This one was a plus. Let's see, I think that there should be, somehow I'm supposed to get a minus here. Don't want to hold this back too long. Yeah, because there's this is going to be, this should end up having a minus on the outside here still. So it should have been minus, minus, get a plus in here. Well, somehow I messed up a sign. And you can go through the derivation again on your own to try to find where that sign difference is. But the key is that you have this boundary term. Right? Here's this thing that we want. Here's a boundary term, and here is this other odd term. So we don't necessarily know what the sensitivities are to be able to then calculate. We don't know DUDP, and so it'd be difficult. This is actually what we would need to calculate the forward sensitivities to do, right? So remember in homework 2, we needed forward sensitivity analysis. You calculated your forward sensitivities, and that's how you then got the derivative, right? Because you directly calculated the forward sensitivities, and then you took the derivative of your cost function by using these values. But remember that the difficulty with that is that, if you have du dp, then you necessarily have m times p terms because you have the derivative of each state variable with respect to each parameter. So we want an equation that has none of this. So what we did was we collected all of them over into one term. And now what we're going to do is we say we want to get rid of that term, because if that term doesn't exist, then we don't have the m times p term. Very similar to what we did with the nonlinear system, right? Where he said, if we do this, then we have an m times p term. So let's do this instead. Like, let's change our parentheses. Once again, we're changing our parentheses, right? So we're saying, we add 0, we move things around, and here we change our parentheses. So if we want to completely get rid of this s term, we need to make sure that this integral is always 0. So let's impose that. Let's impose that lambda ast prime equals minus this plus this. There's a sign error in here. I'm gonna have to fix my notes. And the homework will have the correct one written out. They definitely have different signs between the two. But okay, well, I mean, there's just a minus sign missing in here. So do the hunt for the minus sign. But it's not the biggest deal, right? Basically, the major point here is that to make this term equal to 0, so that way we get rid of all of our m times p terms, then what we would need to do is we would need that lambda star is the solution to this ordinary differential equation. Because if that is true, then this is identically equal to 0. Now, what do we do with this term? This also has an s involved in it, right? So we need to make this equal to 0. And so what we can impose here is we can impose that lambda ast of t is equal to 0. Now, why do we do that instead of the other side? Well, because remember that the sensitivity, the derivative of the solution with respect to the parameters at time equals 0, remember that was one of the things you had to figure out in your first homework problem. That's 0, right? So you start the sensitivities by using 0 as that initial condition because it's 0 with respect to the initial point. So we already know that s of t0 is equal to 0. That's the key from the last homework. So here, though, s of capital T is not necessarily equal to 0. In fact, it's most likely not 0. But if we make lambda of capital T equals 0, then that boundary term goes away. And so if that's true, then everything only is this first term. This first term becomes our entire calculation. EGTP equals So how, so remember that in the nonlinear system, what we did was we did a derivation to avoid hitting this term, and our new derivation was solve the nonlinear system forwards, solve a linear system backwards, and then explicitly calculate something. In fact, this equation is exactly the same as the one that we got here. Exactly, well, it's fairly close to this thing. Oh, picked the wrong one. Aha. Yeah, so it's this one, right? G sub p plus lambda star f sub p. G sub p minus lambda f sub p, right? I defined lambda in a way that was not transpose, but if you put transpose here, they're exactly the same thing. So okay, that's a little funny. It's actually not that funny at all because the solution to an ODE is itself a solution to a nonlinear system, is a solution to a nonlinear system defined by an integral. But that's a detail. Okay, so what we have to do then is we need to do a few steps. Right, so in the same way, what we need to do is we need to solve a forward problem, then we solve for lambda, and then we solve for the gradients. So here in this case, what we do is we do step 1 is solve the ODE u prime equals f of upt. Right, so after we solve the ODE, what we do is then we solve the ODE, we solve the ODE for lambda in reverse, starting at t and ending at t sub 0. Now, why do we do this one in reverse? Well, we do this one in reverse because we've specified a ending condition and we don't have a starting condition. So and essentially, this is the initial condition. It's just at the final time, and we run this in reverse. Right. So we start by solving the ODE or so this gives us u of t. And let's assume that we have infinite memory here and we have a very nice ODE solver that gives us a continuous solution. So we know the full U of t, right? Now we solve lambda and the ODE solver is great and gives us the continuous solution lambda of t. So now with the continuous U of t and the continuous lambda of t, now we can solve dg dp equals. And why do these things need to be continuous? Well, because lambda of t is a function of time, and so we need to have we need to be able to compute a full integral over this quantity. But if we could compute the full integral over this quantity, there you go. That's how you take the derivative of a cost function on an ordinary differential equation solution with respect to the parameters. And how you would then define how the reverse mode automatic differentiation rule is you would assume that that cost function is the identity, and then then that means that the output of G is the solution to the ODE. And then if you let capital G be the identity, you run through this derivation and that gives you how to define the reverse mode automatic differentiation rule. So that's a very high level about how you define the ODE adjoint, but it's leaving off some very crucial details. So what are those crucial details? It's how do you actually define, how do you actually solve this equation? Right. Oh, so let's look at a few things here first, right? So first of all, we say that, so let's dig into some details. So first, discrete cost functions. So, the way that we wrote down this cost function, right? We're basically saying that we're doing an integral over all time points of the cost function. But that's not necessarily how you usually do this, right? A lot of times you're saying, I'm going to integrate, I want to solve my ODE, then I want to check my solution at discrete points, and I want to write the L2 difference between my ODE's output and my actual solution, right? Um, in that case, you want to you want all of your cost function to be evaluated at specific time points. Where this is, specific time points have zero weight in an integral. So instead, what you need to do if you're thinking about that is you need to say that my cost function, right? The equivalent way to write that cost function where it's like at time t equals 1, I want to take the difference between my numerical solution and my data, right? And that's my cost function. The way that you'd write that cost function in an integral would be to use the Dirac delta function. Right, so you'd say something like the sum over I equals 1 to n, where n is each of the time points where I have a piece of data, and do the difference between my data and my ODE solution at that time point. Delta p sub I minus t dt. Right, and why do you do this? Because the integral of a delta function is the same as function evaluation, and so this gives you that, right? Otherwise, the weight where otherwise the weight where your cost function is equal to non-zero is 0, right? Because it'd be only at countably many points in the real line would you have a non-zero integral, and therefore you'd have a 0 as your integral, right? And so you need the Dirac delta here to make it so that way your integral is something non-zero if you only want to evaluate it at very specific points. And so that's one thing you kind of have to think about, that when you think about evaluating the discrete points of the solution and writing your cost function as happening to do with discrete points of the solution, you're implicitly thinking about a delta function inside of your loss function. And so, you need to think about, well, what is my little g here? My little g is something that is, take these differences and I have this delta function, right? In which case, when you take the derivatives of little g, for these terms inside of here, you need to make sure that you are keeping around these delta functions. What does that mean? So what is g sub u of t? Well, g sub u of t is going to be 2, right? The data minus u of t, t delta of t sub I minus t, right? The sum of this at each of your deltas. Right, so remember that capital G is the integral of little g, and if we're evaluating our cost function at specific points in time, then we have a delta function, and so the derivative of this g of the integrand with respect to u is going to be this, and you have to keep that delta function there, right? Another way of writing this then is that g sub u of t is equal to 0 if so it's equal to 0 if t sub I is, if t is not equal to one of the t sub I. Otherwise, it's equal to essentially infinity. So what do you do when you have one of these points then? Well, that means that in this ODE solution, when it's going backwards, g sub u is almost always equal to 0. But on a measure 0 set, so whenever you have a data point, it is actually in that instantaneous moment, it is equal to the data point minus the u, right? So what you have to do then is you can think about this as, solve from from capital T to t sub n, right? You solve it to the last data point, and then so you solve the ODE in reverse from capital T to the last data point. At the last data point, you change lambda asked by g sub u, right? Because at that instantaneous moment, you have a non-zero portion that is added to your differential equation because of this Dirac delta function. It makes that very specific point in time have a non-zero value, even for a zero measure in the integrand, right? By g sub u of t sub n. Right? Then you integrate lambda asked to t sub n minus 1. Then change by g sub u t sub n minus 1, right? And you keep on doing this going backwards till you get to the final data point. So that's something to keep in mind, right? So your ODE going backwards is going to be discontinuous, where every single time you hit a data point, you need to bump that ODE by the difference between the data point and the current or the distance between the data point and the solution going forwards, right? Remember, u is the solution of the ODE going forwards. So you have this lambda moving backwards, and every single time you hit what would be a point where you've had data, you look at the forward solution, you subtract it from your data, and that's how much you change lambda, and you continue moving lambda backwards. That's something to keep in mind. And we talked about things like event handling. This is one case where you can use a discrete callback to be able to define that at very given specific points in time, you would bump the equation by a given amount. Right, so discrete cost functions are actually a bit harder than actually doing the continuous cost function. If all of your loss functions were integrals, like the loss of the total energy of the solve or the total energy drift, your life would actually be easier. But if you're trying to fit a discrete data set, then you need to keep this in mind. So, okay, so discrete cost functions is one thing. Let's see. Oh yeah, how do you actually calculate the ODE, the reverse ODE? Right. So this whole thing I've been saying, you just solve that ODE, right? Now let's actually write this out a bit more, right? So lambda asterisk dt d lambda asterisk dt equals minus, right? So df du t, because u is a function of t, remember? And dg du of t. Right, so u is a function of t, so you actually need to, in order to calculate, this is the the Jacobian of f of upt, except at this point u of t, right? Because as you move u around, you have to take the derivative of this at the point u of t. So in order to actually calculate the Jacobian, you need to know u of t. How do you know u of t? Well, u of t, remember, was the solution to the ODE in the forward pass. So u prime equals f of upt. This gives us u of t. So this actually, this actually is where a lot of implementations can start to differ, and there's different reasons, and we can, in a different part of the course, we can come back to why this is the case, and I might do a separate video just about this topic because it's particularly interesting. But essentially, what happens is you need to know u of t in order to calculate this ODE for lambda star. So what are we going to do? Well, the key here is that you can do two things. You can either remember the entire time series for u of t, so you can solve forwards with a differential equation solver that gives you out a continuous solution, and then whenever you want to take the gradient or the Jacobian, you can take the Jacobian, you know, you could take this Jacobian uh, df of this du at any at the given time point t, and you can evaluate u and then calculate the Jacobian, and you can do this at each point. This is what I ask you to do in the homework, because if you use differential it's going to give you a continuous solution by default, and this should be something that's probably the simplest way to do it. Is there another way to do this? Well, one thing that has come up before is that if you do this system of ODEs, so u prime equals minus f of up minus t, right? And you pair this with this other equation. This technically is a way to solve an ODE in reverse, right? So if you're solving u prime equals f of upt, and then you want to figure out how the flow moves in reverse, it turns out that this is the reverse one. And so if you use, if you solve forwards, and then you know your terminating condition because you've already solved forwards to figure out what u of capital T is. So you have this terminating condition, and you know that lambda of capital T is equal to 0 by definition in order to make that term cancel out, right? So then what you can do is you can say, I can make u of capital T, comma, colon, 0. I can make this be my w, and now I have a system of ODEs, which I'm both moving in reverse. So this is called the backsolve method. This is called the interpolating adjoint method. You can get really fancy with this. So this actually showcases one of the fancy ways that people do this to be able to improve stability. So the issue with doing this form is that even though analytically you can always reverse an ODE, numerically it's not necessarily the case. You can find a lot of counterexamples where If you had zero error, this would work perfectly. But if you have non-zero error, then doing this reverse of an ODE actually can explode your errors infinitely fast or exponentially fast. So it's not necessarily a great thing to do if you have if you have a calculation with a positively Lyapunov coefficient or a highly negative one. It doesn't matter because then it's going to be positive in one direction. So generally, so you have the reversing adjoint, which says, well, I'm going to solve this in reverse, but you do have to be careful about its stability. You have the interpolating adjoint, which solves forwards and keeps the entire continuous solution, and then accesses that continuous solution whenever it needs to take this Jacobian. And then you also have checkpointed methods where here this is showing a checkpointed method where instead of saving the full continuous solution forwards, you save the continuous solution at specific checkpoints in time. And whenever you need to evaluate the Jacobian going backwards at a point in the middle here, you can resolve and get a continuous solution from K2 to K3, and you can have this smaller continuous interpolation give you how to calculate the Jacobian. So you never have to store the entire continuous function all at once. You just you just store little pieces and chunks of it. That is one key detail. Just how do you calculate this term? If you can calculate that term, it all kind of falls together. So okay, how do you calculate that term effectively? Well, this is actually kind of interesting, right? Because this is a Jacobian, so this is a Jacobian, and lambda star. I'm sorry if I did not explain my terminology here. The star is just an adjoint, or which is a conjugate transpose, right? So if everything is real numbers, it's just a transpose. So this is so lambda star asked is a vector transpose. So how do we know how to compute a vector transpose multiply? Reverse mode automatic differentiation, right? In fact, it turns out that in fact, it turns out that so how do you do a vector? How do we do a vector transpose Jacobian? Well, remember that vector transpose Jacobian is exactly what we have these pullbacks for, where you put the vector that you're multiplying by in here, and you put the forward pass value up here, and this is the function that you're using the Jacobian for. So in fact, it turns out that this term right here inside of the ODE is equal to, you do math cal. So you do the you use reverse mode automatic differentiation on the f that defines the forward ODE at the value of u of t, and you do that and you pull back the vector lambda star. And it turns out that this use of automatic differentiation is the fast way to calculate this quantity. It's a vector times Jacobian multiply. This one call to reverse mode automatic differentiation will calculate this without building the Jacobian. So in some sense, what you really want to do then is you want to say that my reverse mode ODE is equal to this. Now here's the kind of funny thing, right? If you have a discrete loss function, right, then remember that g of ut is equal to 0 except at points where you bump it. Essentially what this is saying is that this is equal to 0, and my lambda is the solution to the ODE defined by doing backpropagation. So, lambda prime equals backpropagation of f is the thing that I put, is the ODE that I solve in reverse. And that's the thing that I use to be able to define my backpass. And in some sense, that makes sense, right? The continuous backpass is to solve an ODE that is defined by reverse mode automatic differentiation. In some sense, this is some glory, beautiful kind of relationship. Yeah, so this is this other detail then, right? So the three details that you need to keep in mind is how do I handle the discrete cost function? Well, I normally think of g of ut as equal to 0, but whenever I hit a data point, I change my lambda solution by the difference between the data and u of t. How do I actually reverse the ODE? Well, I need to have some way of having the u of t at every point. Either I solve u in reverse, or I keep a whole continuous solution and I ask an interpolation what its values were at a given t. And how do I calculate this term effectively? Well, I use reverse mode automatic differentiation to do the vector transpose times Jacobian multiply without ever building the Jacobian. And this is the method for doing large scale, PD optimization or training a neural ordinary differential equation. So if you wanted to know what is the equivalent to backpropagating an ordinary differential equation, it's you solve the ordinary differential equation forward. You solve the ordinary differential equation defined by backpropagation going backwards, and then you have to perform this integral. Well, okay, there's one last trick in here to mention, and it's that yeah, solving ODEs is solving integrals, right? So how do we see this? Well, you see that you know, let's say we have u prime equals t, right? Then what you do is you take the integral of both sides, dt, dt. And then you would have u equals t squared, right? So it should be no surprise then that integration and ODE solving are very much related, right? Because they aren't just related, they're, an ordinary differential equation is just an implicit integral where you're also putting u on the other side, right? But if you don't have it implicit, you see that it is just an integral. So um, can you use an ODE solver to solve an explicit integral? Well, let's actually look at this, right? So let's say you have, let's say you want to calculate the integral of, I'm running out of things here, so h of t dt, right? From t0 to t. Let's use Euler's method on u prime equals h of t. Right, we'll see that this is the relationship. Because what we really want to do is we want to do the integral here and the integral here. Right, so the solution u to that ODE should be the same thing as the solution to the integral, right? So let's numerically solve that ODE. So if we do u sub n plus 1 equals u sub n, right? So we talked about Euler's method, and we have to have a delta t in here, and then then the function that we'd evaluate would be h of ti, right? And so so now let's solve this all the way across. Right, so we keep on doing step, and what we get then after we do all this is we get our u sub 0 plus the sum of delta t times, or so I equals 1 to n h evaluated at all the t sub i's, right? This is going to be u sub n, right? The last step. So the last step in total is going to be, because un plus 1 is u sub n plus h of t, which is then u sub n minus 1 plus h of ti minus 1, right? So each time you just evaluate, if you're to do Euler's method on u prime equals h of t, something that's only a function of t, then Euler's method turns out to be just adding delta t times h of t each time, and so you can write out the summation. So now, if, this is a big if, right? If u sub 0 equals 0, then u sub n equals the summation. But what is this summation? If you think about it, this is the Riemann sum, right? Euler's method is giving you, this is the Riemann sum. This is the approximation to the integral. So if you use an ODE solver with u sub 0 equal to 0 on a right-hand side, or on an ODE which is only dependent on t, then the solution at the last time point is equal to the integral of the ODE function over the dependent variable. Right. So in other words, if we let, so if this is true and u of 0, or u of t0 equals 0, then u of t equals the integral from t0 to t of h of t dt. Right. So that's a nice trick to be aware of, right? I did it kind of by showing that Riemann sums, but then you kind of have to show that, yeah, when delta t goes to 0, then that converges to the integral. But you can kind of see the derivation here. So what does this mean? Well, this means that right. So remember that when we're doing this adjoint method, we then need to solve this integral. Well, this integral is something only dependent on t if you know lambda. Or so instead, so then the trick here, solving without using integrals, right? So instead of solving for a continuous, lambda asterisk of t, and then using a quadrature to calculate an integral, we can instead solve. Right, so you can instead do, so let me write down the full version of this ODE. So you write down this ODE, and then you also solve mu prime equals to whatever goes in here. Then mu of t equals, what is it going to equal? Well, it's equal to the integral of the right-hand side, but the integral of that right-hand side is precisely dg dp. So now remember that you need to get this term as well. So then, as an appendix to this, if reverse solve, so if you want to do the reverse solve method, it turns out that you get a really nice formula. If remember that it's not always stable, but if you can do it on your problem, you get a really nice formula, which is that minus f of u p minus t, right? Then this is true, right? So you solve u prime equals f of u pt forwards, and then backwards you solve this set of equations all simultaneously, where, oh, sorry, we're solving in reverse, and so when you get back to the initial point, that's the end of the initial. So you solve u prime with u of t sub 0 known forwards, and then backwards you solve where u of t is known, right? Because you calculated forwards, and lambda asterisk of capital T is 0, and mu of capital T is 0, right? Why is this one 0? Well, because this is required to make all the s terms equal to 0. Why is this one equal to 0? Well, because this is what's required to make this integral, or this integral assumption true. Then it turns out that if so if you solve this ODE numerically forwards, you solve this ODE numerically backwards, then what you get as the final term for what you get as the final value for mu is exactly the gradient of your loss function with respect to p. Now, if you want to then complete what the way that the neural ODE paper wrote it down, you just stick the fact that this is the backpropagation, right? And you just say that this right here is backpropagation, and so you use you use that backpropagation scheme inside of here, and then this is exactly the adjoint as written in the neural ODE paper, right? And so this makes sure that anytime that you hit the Jacobian of the right-hand side of an ODE, which is defined by a neural network, you're only ever doing your Jacobians by using reverse mode automatic differentiation, which is something that machine learning libraries know how to do well. So this is a very nice formula. Again, there are a lot of cases which show up where this is not going to be stable because this reversing an ODE is not necessarily stable. So you might need to use a continuous. You might need to use a continuous u of t and then define this term by u of t, or use one of these checkpointing based methods. But essentially, it's these are the many different ways that people write methods for solving adjoints of ODEs. And then this is how you write the reverse mode automatic differentiation rule. That you solve an ODE forwards, you solve some ODE backwards, or take some integral, and you use that to be able to calculate what these terms are. And that is the adjoint rule that would go into a reverse mode library for what would happen when it sees the ODE function, right? And there's a lot of things like this that you have to kind of sit down and derive. So for example, another function which is kind of cool, which is not necessarily a mathematical function, is what is the adjoint of the function that locks a thread? Well, going forwards, you want to lock, and then going backwards, so you do a lock, and then after your calculation, you unlock. In reverse, you want to make that function in that reverse pass is also going to be not thread safe. And so in reverse, you want to hit the lock first, and then you want to hit the unlock. And so it turns out that the adjoint of lock is unlock, and the adjoint of unlock is lock. And you have to kind of do these derivations on ODEs, or you have to do derivations on MPI primitives, but you can find what the appropriate derivative is to calculate the correct things when doing reverse passes of these other quantities. So I do want to end by describing that there's more than just this shooting method for calculating parameters of ODEs, right? So in the second homework, you found that you write an ODE solver, you stick parameters in there, you run the simulation, it tells you how good you did, you change your parameters, you run again, you run again. In this homework, what you're going to do is you're going to implement this adjoint method. So this is why I say you're going to have to take your time. You're going to have to understand this adjoint method. You're going to have to implement this adjoint method to get your gradients and your cost function with respect to parameters, to then be able to do that method where you try parameter, you calculate the gradient, you try new parameter, you calculate, try new parameter, you calculate. There are alternative methods for fitting differential equations, which you should probably know about. So I want to end this lecture by saying, this is adjoints, this is reverse mode automatic differentiation, this is differentiable programming. There's a lot of things that people are talking about in software 2.0 for how this is, changing the world, and et cetera, et cetera. There are other things that you should think about at the same time. So adjoints are useful but what are some other things to keep in mind? One thing is multiple shooting, right? So a multiple shooting technique is where you say I have multiple initial conditions along my time series. And what my cost function is going to be is I do a numerical solve from one initial condition to the next, and I have 2 points of my cost function. For one thing, I calculate how far away the trajectories are from data points. And the second thing that I do is I calculate how far away the initial condition is from a terminating condition, right? So you say, like, let's say we only have double shooting, right? So I have an initial condition and I have a fake initial condition in the middle of my time series. And now what I do is I solve forward from t equals 0 to t equals 1/2. I solve from t equals 1/2 to 1. My Now I say that this is my full solution, right? Those two chunks. But how do I know what my initial condition is for the midpoint, right? Well, what you do is you say that is a parameter itself, and I want to optimize what that initial condition should be. And the way that I'm going to do this is I'm going to say, I'm going to take the loss of my full trajectory against my data points, right? So that's one of my loss terms. My second loss term is that if I found the correct initial condition, then the previous interval going forwards should hit exactly my initial condition at 1/2, right? So, I solve from 0 to 1/2, but that's different than my choice from the initial condition. That difference should be 0, so I'm going to put a loss function term on that difference. So I have my data difference and I have my pseudo initial condition difference. It turns out that this is one nice way to be able to make it more robust when you're doing very long time series. Because if you just kind of take random parameters and you solve an ODE, till 10,000, you might be very far off, and your ODE solver might diverge to infinity. And so making it so that way you're only doing small chunks at a time can make these fitting a lot more stable. So multiple shooting techniques are one thing to keep in mind, where you can then parallelize the ODE solves, and you can use the adjoint methods to do the adjoint, to calculate the derivative in each of the small time chunks. And so even if you use a multiple shooting technique to improve the way that you do your time series estimation, you still can make use of this same cost function, or this same derivative technology. Now, a completely different way is to say, is to do this thing where you say, well, collocation methods. So with the collocation method, what you say is, what I really want is u prime equals f of u t. I have a bunch of data points. Can I get u prime from the data points? Well, if you fit a curve through it like a spline, then you can take the derivative of the spline at those points, and there you get a derivative estimation from data. If you have a derivative estimate from data, then your cost function can be, my C of cost function is directly on the ODE. And you don't even need to use an ODE solver, right? You just say, u of t, u prime of t, and where u of t we know as the data point, u prime of t we know as the derivative that comes from the spline. So this comes from data, this comes from data. We take a guess at parameters, we put that into our model, we calculate the rest of this from data. If we once we know u prime of t, we actually know how to calculate this cost function without doing anything else other than putting our value of our time points into our model, right? So this can be an exceptionally fast way to calculate, to write down a loss function for ordinary differential equations. And the derivative of this requires none of the extra machinery that we did above, because it's just a derivative. The derivative of this cost function is just the derivative of the f with respect to p. It's a much more simple calculation. Why is this not done all the time? Well, think about, for example, if you're missing this data point. If you're missing this data point, then your interpolation is going to be completely off. So if you have sparse data points, you can't do this. But let me actually show you an example in the diffie-q-flux documentation. So you can do variants of this, like a smooth collocation, where if you have a very dense time series, you can fit a regression spline through everything, and now you can get very accurate derivative approximations at every single point in time, and you can fit a neural ODE by making this be your neural network. And you're just trying to say, make my neural network spit out the right derivative terms at each of these data points along here. And if you do this, you get a pretty good solution. At least you might want to just prime it and then resolve it. But um, this is just another thing to keep in mind, that not everything needs to be, oh, I just stick parameters in, I get a solution out of my program, and I take a derivative, right? In a lot of cases, you can think of something a bit more smarter to be able to do as little of that as possible. But even when you do that, you still need to calculate derivatives of some programs, and so you still want to use some kind of reverse mode automatic differentiation. So this has been a pretty long lecture. It's been a pretty deep one and a pretty hard one. And the reason is because doing all these adjoint methods is not easy. And this is why your last homework problem is going to be take what you've learned here and implement something that will train a neural ODE where you're doing the gradient calculation by hand, right? Um, I guess one last thing that I want to leave you with is, how do you actually do this backpropagation using a library like Zygote? So let's actually go to zygote.jl. Right. So when you look at one of these libraries for reverse monotomic differentiation, right, we've explained now that the reason why to use them is because instead of O of MP for the gradient calculation like forward mode is, um, instead you get O of M plus P, right? And this is the reason to use these libraries for reverse mode automatic differentiation. And so the main thing that they always show in the documentation is, how do I calculate the gradient? Is their main use case is for calculating gradients. But how do you do vector Jacobian products, right? Because what we've shown in this course then is that vector Jacobian products are the true underlying what's going on in a reverse mode automatic differentiation library, right? A gradient, as you'll prove in your homework, is just this. Right? A gradient is just one stuck inside of here. So how do we ask a reverse mode automatic differentiation library to do the pullback of f at u of t, and then what value to pull back? Well, you have to go back. You have to go past the front of the documentation. The front of the documentation is for noobs. You're no longer a noob. So let's look into here. If you dig into here, you will find so if you look at here, you'll see this pullback function. So what this is doing is that, so this pullback function, what it returns is exactly what we got from the gradient, right? So remember that when we define the gradient of dot is something that returns the solution of dot, and it returns a function for the pullback, right? When you do zygote.pullback of f at 0.5, right? This is this calculates, y equals sine of 0.5, y equals sine of 0.5, and back equals math cal b. So this is the pullback function of sine at the forward point 0.5. This is a function. So back of lambda is this function. Right, so you can see that the way that the gradient is calculated then is you do the pullback function, right? So you do the function that does the pullback, and then you evaluate the pullback at 1. Right, so my gradient is just a function that uses zygote.pullback to get the pullback function, and it sticks 1 into the pullback function. So how do you do this term inside of the neural ODE case? Well, what you would do is you would do zygote dot pullback of f with respect to u of t, right? So you use the interpolation to find what u of t is. So this will give you this will give you two terms back. This will give you f of u of t dt, and it will give you back a function back. And then what you do is you'd say back of, this function back of lambda. And when you do back of lambda star, then these two lines of code together, right? So zygote.pullback of f, where the forward pass has u, the backwards pass has lambda. This is the this is the pullback function where of f, where the forward pass has u, the backwards pass has lambda star. Right. So you want to skip the automatic differentiation libraries. Front end, you want to go to where they tell you how to do vector Jacobian products and Jacobian vector products, and where it describes that is the underlying tool that you need for doing this kind of calculation fast. So that's a deep dive. Don't worry if you need to watch this video more than once. This is definitely one of the more difficult ones, but you will need to be working on this for your homework, so go over it many, many times, and please come to office hours if you have any issues. Thank you very much.